Hey guys, you're watching Gamma.
Hello guys, welcome back to my channel. This is the spirit of Gamma talking to you today. This is just an experiment, at least the setup for today, which might persist for a couple of videos into the future. With that being said, let's get started. So in this video, unlike the title suggested, we're going to be working with nth order ordinary differential equation. Let me emphasize on linear differential equation. And it looks a little like this. So y n is the nth derivative of y with respect to the variable t plus p1 of t, that's some coefficient, a function of t, n minus first derivative, p2 of t, n minus second derivative, and so on until we reach the first derivative, and then the zeroth derivative, which is itself the function itself, is equal to some g of t. And since we're considering the simplest case first, I'm going to set this g to 0 because we want the system to be homogeneous, like the title of this page suggests. And again, let me just emphasize that this notation is sort of a more compact alternative to the Leibniz notation. But notice it is the nth derivative with respect to the variable t. Okay, now let me define a set of relations. So if I say a1, of course, of t is y of t, and then I say a2 of t is the first derivative, and then if we do this for n derivatives, and again using the same notation as before, it's actually n minus 1 then we can establish certain relationships, because notice how a1 and a2 are connected. a1 prime of t, and this prime is the classic differentiation with respect to t1s, is a2 of t, and you have a2 prime of t is a3 of t, and then an prime of t, well, that's just going to be the nth derivative of y of t, and we can use this equation to get a substitution for the nth derivative. So notice the nth derivative of y is just negative of all of these other guys. So negative p1, n minus 1, p2, n minus 2, minus dot 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 minus n minus 1 first derivative and no derivative. So it's all of these things. So let me just sort of rewrite them. In this case, the n minus first derivative is just an, right? So you just do those appropriate substitutions in. And we have n equations. And having equations is useful because now we can use linear algebra. Why is that? Let me just show you quickly. Well, it's because if you define a matrix, say A of t, just A, no subscript in general, to be just a bunch of these guys, a column matrix, A1, A2, to say AN. If you differentiate this with respect to time, that means sort of taking the derivative of each of these entries. So you have A prime of t, you get A1 prime of t, A2 prime of t, AN prime of t. But if you look at these equations here, we know these are connected to the unprimed variables. So they're equal to some matrix multiplied with the unprimed variables, so A1 of t, A2 of t, then AN of t. And we need to find these entries out based on these equations. So notice A1 prime is 1 times A2 of t. So we have a 0 everywhere else except in the second column because of this A2 present. A 0 everywhere else. So the n minus 1 0 is just this 1 for A2. Because that's how, if you do the multiplication, how this is going to work out. And then there will be a symmetry here. There will be a 1 for the A3 now, because A2 prime is just 1 A3 and 0 everywhere else. And then we can continue this trend to notice that, well, there is zeros everywhere else except we have the last one for the n minus 1. And then for the an prime, we have this last equation. So just instead of having this 0 like 1, we have these coefficients p1, p2, pn with negatives in with them. So whatever is with a1, that's pn. So negative pn, negative p sub n minus 1. Then we have negative p2 and negative p1. And this matrix here, I'm going to call that capital A of t because these coefficients were functions of time. And this is A of t. So what we finally get is A prime of t is just A of t acting on a small a of t. And this is an equation that we need to solve. And how do we solve this? Well, a homogeneous system, if you remember my video with the coupled spring oscillators and systems like those, the approach for something like this is kind of canon. It's pretty standard at this point, or it should seem pretty standard at this point. All you do is you guess, you do an ansatz that A of t is some bunch of coefficients which are independent of time, so amplitude coefficients times e to the lambda t. Why is this useful? Well, the e to the lambda t is sort of the eigenfunction for this derivative with respect to time operator, because if you plug this in this equation, what you get, you differentiate with respect to time, you get 1 lambda out. It's C1, C2, Cn e to the lambda t equals, well, just A of t1, nothing there. And here's C1, C2, Cn e to the lambda t. So you forget whatever was the exponential. And you notice what's happening here. You have A on some vector C, lambda times some vector C. You have an eigenvalue problem right here. The best thing about these problems is that you know how to solve them. It's sort of been over-solved, over-talked about. everywhere. So you set the determinant of this equation to 0, and you find the bunch of lambdas out. So those are your eigenvalues. Once you have the eigenvalues, you can find the eigenvectors. And after finding all the eigenvectors, assuming there's no significant degeneracy in your system, which means there's no two different distinct eigenvectors associated with the same eigenvalue, you can construct a basis, and there won't be, if the problem is well posed, you won't run into such problems. You can construct this coefficient vector from the eigenbases, so the bases that the eigenvectors will span, and they will usually span if they're linearly independent. So you can construct these out of the eigenbases themselves. And well, after you know this, you know what the lambdas are, you can basically write that as a linear combination over the eigenbasis for all eigenvalues, and then that's it. That is your general homogeneous solution for this system. I'm not going through like the steps for like the last part, because I think we talked about this a lot. This is your general homogeneous solution. That's pretty much what you need to do for the homogeneous solution. You have this, just sort of convert this by using this clever coupled system of equations. Define a column vector, get this equation out of it, find the coefficient matrix based on these equations, and then just it becomes a classic eigenvalue-eigenvector problem like we dealt with in the coupled oscillator before. Find the eigenvalues, get the eigenvectors, get an eigenbasis, represent the coefficients or the amplitude vector as a linear combination of the eigenbases, and that will generate your homogeneous solution in the most general form. Moving on to the not so obvious non-homogeneous solution. So moving on to the non-homogeneous solution, well, the system is as it is before. I've literally changed nothing else. The g of t is not 0 in this case. So what are we going to do? Well, let's first just redefine the problem a little bit. Let's say, maybe let me choose a different color. Setting colors can be a little confusing sometimes. Okay, so u1 of t, I'm going to define that as y of t. u2 of t then just becomes first derivative of y with respect to t. u3 of t just becomes the second derivative of y with respect to t. And then un of t just becomes n minus first derivative of y with respect to t. Well, fair enough, with this definition, like before, you get these coupled systems. u1 prime is u2, u2 prime is u3, un prime is just, well, un is the n minus first derivative, un prime will be the nth derivative, and we can sort of make the nth derivative of y the subject of this equation. So you get negative of all these guys. So you have negative p1, n minus first derivative, that's just un, minus p2, n minus 1, minus dot dot dot, pn minus 1, u2, pn u1, but this time we also need to tag along this g of t factor. which I'll just write as G. And then U prime of t can be represented as, like before, some coefficient matrix A of t multiplied with U of t plus B of t, because the thing is G is not associated with any of the U's. So it's sort of like a stray factor, and we need to account for that with this B term. This indicates in general that this system of equations that we're trying to solve is associated with a non-homogeneous problem. So then U of t, of course, is U1 of t, U2 of t, Un of t, this column vector. Well, A of t, the coefficient matrix, is like before. Literally nothing has changed. I mean, you find this out by looking at these equations. You need a 1 for the U2. So 1 on the second column, 1 on the third column, and then finally the 1 in the last column. And then the last row is just these coefficients, nothing fancy about it. And then, of course, this extra definition for the B of t. Well, the G comes in only for the very last row. So there's 0 everywhere else, except for the last row, which has the G in it. Now, let's do something that's slightly more creative, in the sense that, well, we didn't do this for the homogeneous solution. We're doing it for the non-homogeneous case, of course. This entire thing merited an extra procedure from the very start. Capital Y of t, I'm defining that to be y1 of t, y1 prime of t, yn minus first derivative of y1, then y2 of t, I'll do the same, differentiate that once, n minus 1 times, and then yn of t, yn prime of t, yn differentiate n minus 1 times, still a function of t. Well, this kind of looks similar, and I just need to clarify one thing. y1 to yn are the homogeneous solutions to this equation. So if you remember the previous page, we defined them as a with the as small a. Here we're calling them y, but these are the homogeneous solutions that you get from the method defined on the previous page of eigenvalues, eigenvectors. Okay, so this sort of looks like the Wronskian matrix, or to put it more succinctly, the Wronskian quantity in n dimensions, because it's an n by n matrix, is the determinant of this guy. So Wronskian is just the determinant of y of t. That's the succinct way of putting it. How does this help? Because we are assuming that the solution that we look for, the U's which are the solution for the non-homogeneous system, are just these homogeneous solutions, but weighted by a factor. We call that W of t. So of course W of t has n entries, W1 of t, W2 of t, Wn of t. So these are the weighting functions. And of course, we're not doing a linear combination of homogeneous solutions. W is a function, it's not a constant, so it's not a linear combination, and that's why we won't end up with necessarily a homogeneous solution. This should be the heterogeneous, non-homogeneous solution. Now, we can sort of plug this into this equation. So u prime, just use the product rule here. Y prime of t times w of t plus y of t, w prime of t is equal to a of t acting on u of t, where u of t is now y of t w of t plus lone factor b of t. One interesting thing to note is when you apply a of t on y of t, if you apply a of t on this, that's like saying if you take one column from this, the column of the new matrix that is generated after this multiplication is just a acting individually on this column. So you can look at each individual column and say, well, the column for the new a times y is just the matrix A acting on the first column. So the first column of, let me write this down, the first column of the product matrix AY is the matrix A acting on the first column of Y, the original Y. So that's like saying first column of AY. So whatever you're going to get is A acting on this guy. So if you let A act on this guy, if you notice what's going to happen, it's gonna prime everything up, because that's what A does, right? I mean, if you look at how A was defined, it just primed everything up. Like U1 became U1 prime because of the action of A. So Y1 will become Y1 prime. Everything will just get differentiated once with respect to time. That's by how the system we had here is constructed, or how this differential equation is in general. So I hope that convinces you. Can multiply each, you can do this multiplication of AY and see that you indeed get a Y prime of t out of it. So we have this Y prime of t here, W of t, B of t. But notice the nice thing, this cancels out with that, which means Y of t times W prime of t is equal to B of t. So this just becomes a problem that is like matrix acting on vector gives another vector. This becomes one of those problems. And remember, in the last video, we talked of Cramer's rule, and mind you, everything on this channel is for a reason, and I chose the order of introducing this in the last video, however dry the topic was, because of this applicability here. The solution, the jth entry, was the determinant of the modified matrix, where the jth column of A is replaced by B, divided by the determinant of A. This was the Cramer's rule solution. We're going to apply that here. In case of X, we're going to generate Wj prime of t, because we had that in this equation, to be the determinant of the modified matrix. So Y with the jth column replaced by B of t, which is still a function of t, divided by the determinant of Y of t. But remember what the determinant of Y of t was. It was just the Wronskian itself. So maybe just make like a stylized W. Now, since we have a prime here, how do we get rid of that? We'll just do an integral in time. So you have this determinant divided by this, which is the Wronskian. itself dt. What we can do is, notice yj is just the matrix y with the jth column replaced by b of t. Well, b of t is just it's just 0, 0, and then 1 times g of t, right? That's what b of t is. Well, now what I'm gonna do is I'm just gonna replace the jth column by this identity, by this basis kind of looking vector, and we're going to multiply g outside separately. So we're going to call that matrix that as with a prime, so y sub j prime of t divided by determinant of y of t times, now that I pulled the g of t out, right, as I claimed, that would be your weighting function. You have your weighting function, you have your homogeneous solution as discussed before, so we can get the non-homogeneous solution out of it using this relation, and then we're done. One thing to note is this form, it looks similar to the simple n equals 2 case, the second order linear differential equation case. So where the particular solution was y2 integral y1 driving function over Wronskian dt minus y1 integral y2 driving function over Wronskian dt. Here the driving function is g of t, that's why I pulled it out. Wronskian, well, we indeed have that in the denominator, so don't need to worry about it. We discussed that before. That's how we define the matrix y of t. These y1, y2 were homogeneous solutions back then. They still are now, because this matrix is the homogeneous solution matrix. Mind you, this prime is not a derivative. I'm just saying that this is a different, not put a prime, this is the matrix y with the jth column replaced by 0, 1. Again, this minus sign is because of the determinant. If you work through the calculation and the cofactor part of the determinant, I'm sure you get this negative sign between them, and everything will work out. You can just sort of do a sanity check with n equals 2, and you should get the same result out. So this is what's nice about this. We've generalized the Wronskian approach and just shown you how powerful it is. What's important to note is how we converted this linear differential equation, and again, the keyword is linear. Without linearity, we wouldn't have been able to get back to linear algebra, and that's why it's called linear algebra. We've connected linear differential equations with linear algebra, so that's one thing that's really nice. People don't realize how nice and beautiful this is. And just make a mental note of this method of converting. By redefining all the derivatives with these quantities, we've introduced these relations. Well, the first relation seems trivial, right? I mean, u2 is the first derivative of y, which is u1, so u1 prime. It is a trivial relationship, but it is still useful for us when we're finding the coefficient matrix out. And that's how we roll. That's it for this video. Do like and subscribe to my channel, guys, and do let me know in the comment section what you feel about this new voice. Does it make me sound confident? Do you understand it, or do you prefer my natural voice? So, of course, comment section is always open. Feel free to share your opinions. In the meantime, stay home, stay safe, keep doing math, and peace out.